Welcome students of B Civil for the subject Advanced Concrete Technology Unit number 4. It includes historical development of fiber reinforced concrete, properties of metallic fiber, polymeric fibers, carbon fibers, glass fibers, basalt fibers, natural occurring fibers, and interaction between fibers, they are uncracked matrix, interaction between the fibers, the cracked matrix, then basic concepts, mechanical properties, the tension, and another mechanical property is the bending. Now we will see the properties of metallic fiber, polymeric fiber and carbon fibers. First we will see properties of metallic fiber. The definition of metallic fiber. Technically, a metal fiber can be defined as a manufactured fiber composed of metal, plastic coated metal, metal coated plastic, or a core completed covered by metal. In other words, a metal fiber is any form produced from metals which may be alone or in conjunction with other substances. A metal fiber can be distinguished from a metal filament by its diameter. For example, within Becquerel filaments below 100 nanometer in diameter are considered as fibers. We will see the brief history of metal fiber. Metallic filament and yarns have been used for more than 3000 years. Gold and silver were hammered into extremely thin sheets, cut into ribbons and worked into fabrics. Examples include magnificent Persian carpets and Indian ornamental saris. Down through the centuries, kings and queens have worn garments that have glittered with gold and silver fibers twisted or wrapped around cotton or some other thread. In the mid-20th century, the more industrialized use of metal fiber in various applications began when the Dock Gum Company produced the first modern metal fiber in 1946. During the early 1960s, conducted a research program to develop an economical process for forming metallic filaments, then started producing metallic filament in a laboratory scale pilot plant. By 1964, produces fine metal fibers as small as 1 nanometer from 304 type stainless steel. The 750,000 pound per year metal filaments plant in Michigan, USA was brought on stream in 1966. Metal fibers are now widely produced and used in all kinds of technology. It's a mature sector with a wide range of applications. Now we will see the properties of metallic fiber. Thanks to give the good electric and heat conductivity, high corrosion and thermal resistance, and excellent EMI, that is electromagnetic interference, and ESD, electrostatic discharge, shielding capabilities, stainless steel fibers are used throughout numerous consumer and industrial applications in diverse fields. Ferric alloy, iron, chromium aluminum alloy fibers are even more resistant to high temperatures and are often used in vehicle exhaust pipe and high temperature filtration felt and burners. Nickel displays resistance to chemicals, acids and alkalis, and good electric and thermal conductivity, making it suitable for diverse applications. Metal fiber structures and products display excellent properties such as high porosity, which benefit the function and structure of specific application. Their low electrical resistance makes them suitable for any application that requires electrical conductivity. Excellent thermal resistance makes them withstand extreme temperatures, while corrosion resistance is achieved through the use of high quality alloys. Other advantages, mechanical properties of metal fibers include shock resistance, fire resistance and sound insulation. Metal fiber can be used as reinforcement fiber for composite materials, improving braking behavior upon impact and electrical conductivity. Traditional carbon or glass fiber reinforcement fibers have been limited very possibilities which results in a brittle and explosive braking behavior. Metal fiber act perfectly complementary to this and can absorb much more energy before breaking. Processing is no different from any other reinforcement fiber for composite material. It is even possible to combine metal fiber with other fiber into a hybrid composite structure which combines all the benefits of carbon, glass and steel. The properties of metallic fiber, the property is the length. This is the Dramix OL 13/20 and another is the Dramix 3D 55/30 BG. The length is 13 millimeter and here another is the 30 millimeter. The diameter is in millimeter 0.21 and 0.55. Flexural strength of the Dramix OL 13/20 metallic fiber is 2750 and Dramix 3D 55/30 BG is 1345. The dosage to be given for the concrete in kg per meter cube is 60 and another is the 25. Modulus of elasticity in GPa gigapascal it is 200. So this is the figure for the Dramix OL 13/20 and this is the figure for the Dramix 3D 55/30 BG. We have seen the properties of metallic fiber. Now we will see the polymeric fibers. Polymeric fibers, in the last few decades, the interest in the use of polymers as replacement for other materials such as metals, wood and ceramic has increased significantly. This is due to the advantages that polymers offer over conventional materials, including ease of processing, productivity and cost reduction. The polymeric materials have to be reinforced in order to meet the high demands on strength and stiffness for many applications in aerospace, automotive, electrical, microelectronics, infrastructure and construction, medical and chemical industries. The use of conventional fillers such as glass or carbon fibers have received much academic and commercial attention in the past. Although excellent mechanical properties have been achieved in this way, life cycle assessment does not yield favorable results for traditionally reinforced composite due to limited recyclability and high energy requirements of their end of life process. Furthermore, current environmental legislation and waste management regulations aim to encourage manufacturers of the materials and end products to consider the environmental impact of their products at all stages of their life cycle, inclusive of recycling and ultimate disposal. This fiber provides some specific features such as recyclability, ease of production, low cost, low density and good interfacial bonding without any surface treatment. Increase in mechanical properties of the fibers can be achieved via molecular orientation during spinning and drawing. The development of high stiffness and strength polymeric fibers are required to impart high mechanical properties. So the properties of polymeric fibers we will see here. The types of the fibers: ultra high molecular weight polyethylene, density is 0.96 gram per centimeter cube. The tensile strength in megapascal is 2800. Another is the polyethylene. The density is 0.96 and the tensile strength range between 1000 to 1500. Produced polypropylene, the density is 0.9 and tensile strength is 650 megapascal. All produced polypropylene tapes, density is 0.732 and tensile strength is 450 megapascal. This is Vectranium, the density is 1.396. Vectran HS 1.403 is the density in gram per centimeter cube. The glass, the density is 2.54 gram per centimeter cube and the tensile strength in megapascal is 3000. And the carbon, the density is 1.8 gram per centimeter cube and the tensile strength of the carbon fiber is 3600 megapascal. So these are the polymeric fibers. We have seen the polymeric fibers. Now we will see the carbon fibers. What is carbon fiber? Carbon fiber, not surprisingly, is made of carbon crystal aligned in a long axis. These honeycomb-shaped crystals organize themselves in a long, flattened ribbons. This crystal alignment makes the ribbon strong in the long axis. In turn, these ribbons align themselves within the fibers. The fiber shape is the original shape of the material. Its precursors used to produce the carbon fiber. Fibers are shaped after carbonizing. These fibers containing that flat ribbons of carbon crystal in turn are bundled by the manufacturer in thicker fibers and are woven into carbon cloth made into felt, twisted or bundled without twisting. This is referred to as roving. Carbon fiber is also offered as chopped strands and powder. We will see now the manufacturing of the carbon fiber. There are several methods of making carbon fiber, but essentially they all begin with the making of fibers out of a carbon-rich precursors material. The original size and shape of the fiber will remain in the finished carbon fiber, but the interior chemical structure will have been greatly modified through the various heating cycles. The first step are carbonizing and stretching precursor fibers, either PAN, that is polyacrylonitrile, pitch or rayon. There are several cycles of heating at varying temperatures excluding oxygen. This process drives off most of other elements, hydrogen and nitrogen mainly, of the starting material, leaving carbon behind. It also allows the carbon to gradually crystallize in its characteristic honeycomb way. Proper alignment of the carbon fiber is essential to maximize their benefits. Now we will see the properties of carbon fiber. First, the high strength to weight ratio, also known as the specific strength. The strength of the material is the force per unit area at failure divided by its density. Any material that is strong and light have a favorable strength to weight ratio. Materials such as aluminum, titanium, magnesium, carbon and glass fiber, high strength steel alloys all have good strength to weight ratios. The examples are given. The carbon fiber, it is having 2457. Glass fiber is having 1307, spiral silk is having 1069, polypropylene is 89 and nylon is 69. PAN based precursor carbon fibers has higher strength than pitch based carbon fiber which has higher stiffness. The second property of carbon fiber is the rigidity. Rigidity or stiffness of the material is measured by its Young modulus and measures how much a material deflects under stress. Carbon fiber reinforced plastic is over 4 times stiffer than glass reinforced plastic, almost 20 times more than pine and 2.5 times greater than aluminum. Remember, stress is the force, strain is the deflection such as bending or stretching. The third property of the carbon fiber is the corrosion resistance. Although carbon fibers themselves do not deteriorate measurably, epoxy is sensitive to sunlight and needs to be protected. Other matrices, whatever the carbon fiber is embedded in, might also be reactive. Carbon fibers can be affected by strong oxidizing agents. Composites made from carbon fiber must either be made with UV, that is ultraviolet resistant epoxy, uncommon, or covered with a UV, that is ultraviolet resistant finish such as varnishes. The fourth property of carbon fiber is the fatigue resistance. Resistance to fatigue in the carbon fiber composites is good. However, when carbon fiber fails, it usually fails catastrophically without significant exterior signs to announce its imminent failure. Damage in tensile fatigue is seen as reduction in stiffness with larger number of stress cycles unless the temperature is high. Tests have shown that failure is unlikely to be a problem when the cyclic stresses coincide with the fiber orientation. The fifth property of the carbon fiber is the good tensile strength but brittle. Tensile strength or the ultimate strength is the maximum stress that a material can withstand while being stretched or pulled before necking or failing. Necking is when the sample cross section starts to significantly contract. If you take a strip of plastic bag, it will stretch and at one point will start getting narrow. This is called as the necking. Brittle materials such as carbon fiber does not allow fail at the same stress level because of the internal flaws. They fail at small strengths. Tensile strength is measured in force per unit area. The unit is in megapascal. The carbon tensile strength, a carbon steel of 1090 grade is 650 megapascal. Polypropylene is ranging between 19.7 to 80. High density polyethylene is 37. Stainless steel AISI 302 is having the 860 megapascal. Carbon fiber alone it is 4127. Carbon fiber in laminate it is 1600 megapascal. The fifth property of carbon fiber is the fire resistance or not flammable. Carbon fiber is classified as non-combustible and has no listed flash point. If it is exposed to high heat in the presence of fuel burning, it can eventually oxidize, but as soon as the flame and fuel is removed, the flame does not continue. Because carbon fiber is almost always used in the matrix such as epoxy, plastic or concrete, the tolerance of the matrix to high temperature is more significant factor. Depending upon the manufacturing process and the precursors material, carbon fiber can be made to feel quite soft to the hand and can be made into or more often integrated into protective clothing or firefighting. Nickel coated fiber is an example. Because carbon fiber is also chemically very inert, it can be used where there is fire combined with the corrosive agents. The seventh property of the carbon fiber we will see here, the carbon fibers are brittle. The layers in the fibers are formed by strong covalent bonds. The sheet-like aggregations readily allow the propagation of cracks. When the fibers bend, they fail at very low strain. In other words, carbon fiber does not bend such before failing. So this is the figure of the carbon fiber. So we have seen the properties of metallic fiber, polymeric fibers and the carbon fibers. So these are the YouTube links available on the YouTube. Dramix steel fiber in precast. Another is the steel fiber concrete reinforcement, how it works. Next is the price comparison steel fiber versus traditional concrete reinforcement. Another is the polymer fiber for concreting reinforcing, Bautech. Next is the Sika Carbodot carbon fiber structural strengthening of concrete structures. Next is the smart concrete with carbon fibers. Next is the Halifax Bridge carbon fiber reinforced beam. Another is the carbon concrete manufacture and testing. Another is the how it's made carbon fiber. So we have seen the properties of metallic fiber, polymeric fibers and the carbon fibers. The unit 4 includes historical development of the fiber reinforced concrete, properties of metallic fiber, polymeric fiber, carbon fiber, glass fiber, basalt fiber, naturally occurring fibers. It also includes the interaction between the fibers, interaction between matrix and cracked matrix, interaction between the matrix, that is the cracked matrix, the basic concepts, mechanical properties, that is the tension, and another mechanical property is the bending. So thank you all students. Please give me your attendance if you have viewed the video as video topic _ division _ roll number _ self name.